All right, guys, welcome to Stats 4.2. We're going to be talking about compound events and probabilities today. So to start off, talk about what are called independent events. Now, you've likely heard a lot of these terms before, but I want to kind of go over them as if you haven't. So what independent means is that it is not affected by anything which has happened already. So for instance, if I take a die, right, and I roll this die, and I get a 6, right? The probability of me rolling a 2 on my next roll is not affected at all by the fact that I just rolled that 6, right? So that's independent. There's nothing it's not affected by what happened previously. On the other hand, if I take a deck of cards, right, and I shuffle it a bit, I draw out a 7, right? Me drawing out this 7 has now changed the probability of me drawing an ace now, right? If that 7 was still here and I was all shuffled, right? Probably of me drawing an ace is 4 aces out of the 52 cards. I draw out this king. Now my probability has changed, right? Because of what I just did, the probability of me drawing an ace is now different than it was previously. So that is dependent, whereas we're talking about independent right now. So if we're independent, stuff's a lot easier for us, okay? So if I try to figure out the probability of two independent things happening together, it's just I take those two probabilities and I multiply them together. So for instance, I want to draw a 7 from my deck, and I want to roll a 2, right? Me drawing a 7 does not affect the roll. My roll does not affect my draw. So they're independent. So I just take this probability times this probability, and I get my total of those both happening at the same time. So the more general rule, if they're not independent, is this, right? We say the probability of A happening times the probability of B happening given that A has already happened. That's what this notation means. This is the probability of B occurring assuming that A has already occurred. So for instance, my drawing cards example here, right? If I wanted to draw a king and then draw a 7, right? The probability of drawing a king is 4 out of 52. Then my probability of drawing a 7, assuming I've already drawn a king, so if I've already drawn this king out, right? So that's already happened. Now my probability of drawing the 7 is 4 out of 51, because there's 51 cards left and 4 of them are 7s, because one of them has already been taken out, and that's the king, right? So that's how I could do those kinds of things. So that's what that notation means. Probability of this happening given this has already happened. Okay. And then for conditional probability, how I can find that, one of the methods is find the probability of both of those happening at the same time, and then I can divide by the probability of the event that already happened having happened. So basically all of this is me taking this equation here, and I'm dividing by the probability of B happening. So that's what you're seeing. This is basically this, but just solved for a different variable, right? Okay, so let's try one of these out, okay? So Andrew is 55, the probability that he will be alive in 10 years is 0.72. So once again, sorry that this is a bit of a morbid topic, but here we go. Ellen is 35, and the probability that she will be alive in 10 years is 0.92. So what is the probability that both of them are going to be alive in 10 years? So first of all, these are independent events. We're going to assume that these aren't people that are living together and spending time together and might be affected by the same car crash or something along those kinds of lines, right? So they're entirely independent. So to find out the probability that Andrew is alive in 10 years and Ellen is alive in 10 years, I just take those and I multiply them. So 0.72 times 0.92, I get 0.66. So there's a 66% chance that they're both alive in 10 years. Okay, so dependent events. So this is like I mentioned, this is affected by what has happened previously. So and this is a very common case for these things. This is kind of a quality control type of example here. So we have digital camera flashes and digital flash cameras, and they have a lot of 100, right? So if they randomly draw 2 of those 100, right, and both of them are defective, then they toss out the entire lot because, hey, there's enough of these that are a problem, which we're going to just assume that all of these are bad, or most of these are bad enough to cause problems. So if 10 of those are defective, so let's, for this case, assume we know that 10 out of the 100 are bad, right? So let's walk through this problem. What's the probability of getting a defective camera on the first draw? There's 10 bad ones out of 100. That's 10 over 100. I could reduce it to 1/10, but I'm going to leave it as 10 over 100 for a reason which you'll see here in a second, right? So the first camera draw is not replaced. So I found it. Hey, there's my first camera. I put it aside. Now I randomly draw my second camera, right? So now there's only 99 cameras left for me to choose from, right? What's the probability of getting a defective camera on the second draw if the first camera was defective? So I drew out one of my 10 defective cameras. So there's 9 defective left out of the 99 total, right? So now my probability is 9 out of 99 for drawing my second camera and having that be defective, right? So first one was 10 out of 100, and then 9 out of 99, right? Are these probabilities in events A and B different? Well, yeah, I'm going to get one will reduce down to 1/10, and the other one will reduce down to 1/11, right? Does drawing a defective camera on the first draw change the probability of getting a defective camera on the second draw? Are the events dependent? So let's say I did not draw a defective camera on my first draw. Right now there's 10 out of those 99 which are a problem. So now my chance of getting a defective on my second draw is 10 out of 99, not 9 out of 99. So since that does change the probability, it is dependent, right? That's the big thing which we're trying to kind of showcase here. So then finally, I use our formula for dependent events. Probability of A and B is equal to probability of A given times the probability of B given A. So if we do that like we said, we're going to have 1/10 times 1/11. That's after we reduce those, so we get 1 over 110, which is a 0.009-ish in your chances. So again, a very, very low chance of that occurring. Okay, so combining events here, so probability of A or B. Okay, so what or means in this context is either A happens, B happens, or A and B happen together. Okay, so that's what or means. It doesn't mean that it's A or it's B and not both those together. It's A or it's B or it's A and B. Okay, that's what or means for us. So let's try and deduce which of these situations is an and, which of these is an or. And so go ahead and pause and read through these bottom half and determine, hey, is it talking about and a occurrence and or an or occurrence? All right, so satisfying the humanities requirement by taking a course in history of Japan or by taking a course in classical lit. The word or is in there. It's pretty obviously an or condition there. B, buying new tires and aligning the tires. So again, that's going to be an and because it has the word and in it. That makes it pretty easy. Then getting an A not only in psychology but also in biology. So that is an and a occurrence. This is me trying to purposefully write it without the words and or, so that you can kind of think more about the situation, not just looking for the words, right? Then having at least one of these pets: cat, dog, bird, rabbit. So that's an or, right? Because it could be a cat, it could be just dog, it could be dog and bird, it could be rabbit and cat, it could be any kind of one of those crazy combinations which we could have there, right? All right. So this brings up the idea of what's called mutually exclusive, or also called a disjoint event. So two events are mutually exclusive if they can never happen together, right? So for instance, on my deck of cards, let's say I want to draw a face card and I want to draw a 7, right? I cannot draw one card and have it be both a 7 and a face card at the same time, right? So those are disjoint events. They're mutually exclusive because they can't occur at the same time. Okay? That's what disjoint means, right? So our rules for addition in mutually exclusive sets is really, really easy, right? We just literally add the probabilities, right? So I say, hey, here's my probability of a face card plus my probability of a 7. I add them up, done, right? So it's really easy if they're mutually exclusive, kind of like the multiplication rule was really, really easy when they were independent. But we also have the general rule in case they aren't mutually exclusive. That is the case here. Still, the probability is being added, but then we also have to subtract off the probability of them both happening at the same time. So if I talk about drawing cards still, right? I say I want the probability of drawing a red card or of drawing a face card. Okay, so my probability of a red card is half of the deck, right? So that's 26 out of 52. Then my probability of drawing a face card is 12 out of 52. So but I can't just add those up, because if I add those up, there's certain cards which are being counted twice. All of my red face cards are being counted in my probability of drawing a red. They're also being counted in my probability of drawing a face card. So I'm counting those twice, so I'm getting more than I need. So that's why I have to subtract the overlap, which is the probability of red and a face card. So there's 6 red face cards. So I would want to then subtract off 6 out of 52 to balance that out, because then I don't have that overlapping portion. So that is what that kind of last bit there is for. So that's how we deal with things that aren't mutually exclusive. It's a little bit more work there, but not a huge deal. Okay, so let's try this out. So go ahead, pause the video, read through that, and then try to answer these questions. All right, so we're buying pants. We have a 30% chance that the pants are too tight and a 10% chance that the pants are too loose. So can our pants be too tight and too loose at the same time? We're going to say no, they cannot happen at the same time, so they are mutually exclusive. I understand that maybe the pants are too tight in the waist, but they're too loose in the leg, or some weird combo. Don't overthink it. It's just a sample problem. Okay, so they're mutually exclusive for us. So if I want to find the chance of a pair of slacks being either too loose or too tight, I can just add those up. So 0.3 times plus 0.1 is equal to 0.4. So there's a 40% chance that the pants won't fit. Right. So, all right. Now let's try this. So, Ms. Jackson is in charge of a program that helps people for a high school equivalency exam. She shows that 80% of students need to work in math, 70% need to work in English, and 55% need work in both areas. So are needing help in math and needing help in English mutually exclusive? Well, no, right? Because it's possible to need help in both, and in fact, they tell us that 55% of people need help in both, right? So now we can use our formula to figure out, well, how many people need help in math or English. So that's going to be the probability of needing help in math plus the probability of needing help in English minus the overlap, which is that 55%. So 0.8 plus 0.7 minus 0.55, and that's going to give us 0.95. Right? And that also kind of brings up a really red flag case of, hey, this was not mutually exclusive when I treated it like it was. let's say we didn't think that, let's say we thought that this was mutually exclusive and said, well, then this 0.8 plus 0.7, hey, that's 150% of people. That's a red flag, and that's more than you can have, so you likely missed that overlap which you needed to subtract off of it. Okay, let's take a look at this in a slightly different context here. So here we have a chart, and this is a chart kind of view as opposed to, hey, here's what the actual numbers are. So we're going to try and answer these questions. So go ahead and pause and try and answer those 4 questions in regards to this table. Okay, so first of all, let's find the probability that we're independent and the probability that we are working in production. So the probability that I am independent, well, that is 17 people out of the 140 total, right? Probability that I work in production is going to be 92 out of the 140 total, right? Now, the probability that I am independent, assuming I work in production. Okay, that's what that means. So out of only those that work in production, that's out of 92, 8 are independent. So that's 8 out of 92 is my probability of being independent given I work in production. Then, how about the probability of me being independent and in production? Well, that's only going to be 8 people out of the 140. Okay, so we can see how that's a little bit easier in this kind of chart format here. Then we say, what's the probability of us being independent or in production? So I want to find the probability of being independent, which I found earlier, plus the probability of me being in production, which I found earlier, minus that overlap of 8 out of 140. And when we do that, we should get about 0.721 for our total there. Okay, so with that, here is 4.2. We're going to be doing 1 through 2, and then 3 through 51's just the odds. I know that seems like a lot of problems, but when we're in this probability stuff, it's a lot of really short, relatively easy questions for us to be answering. So talk to you guys next time.